Math 2312, section 1.6, excuse me, wrong class. Section 1.6, which was absolute value equations and inequalities. Absolute value equations and inequalities. And in this video, I'd like to do another example of an absolute value inequality. In class on Thursday, September 10th, we did an absolute value inequality at the end, and I gave you a universal approach for pretty much any inequality, but we only got one example. So I thought I should do it a little more justice and make a video or two or three demonstrating a few more examples. So let's take a look at this one. Solve the absolute value of x minus 1 over 5 is greater than 2. Now, if you look in most college algebra or pre-calculus textbooks, they'll give you a technique specifically for absolute value greater than a constant. But that technique is specific to this type of problem. So I'm going to remind you, or rather demonstrate again, the more universal technique that always gets the job done. Now, one thing I didn't say in class yesterday is when you have a technique that works universally on a larger class of problems, it usually takes longer to do. Whereas techniques that are tailored for a specific problem are shorter. So it's a choice between, do you want something that takes less time but only works here, or do you want something that takes more time but works almost every time? I choose the second. I would rather have one technique that works all the time, even if it takes a little bit more time. And then as you do more math, you start focusing on techniques that are specific to certain situations for the sake of saving time and space. But let's focus on that general approach, that universal approach to solving pretty much any inequality. The first move in that was to pretend it says equals and solve. Now, how easy or difficult this move is depends upon the type of inequality and hence the type of equation you have. And in this case, we have an absolute value equation, which we've discussed quite a bit. The general technique was if you have the absolute value of an expression equal to a number, as long as that number is non-negative, then you rewrite this two ways. You set the inside equal to that number, and you also set the inside equal to the opposite of that number. And the reason was pretty straightforward. Whatever's inside this absolute value has to give me an answer of 2, and there's only two numbers that do that, 2 and negative 2. So the thing inside the absolute value has to equal 2 or negative 2. And then how you finish solving this depends upon the type of equation. This one's pretty straightforward. Multiply both sides of both equations by 5. If I multiply both sides of the first equation by 5, the 5's cancel on the left. On the right, I get 2 times 5 is 10. And if I multiply both sides of the second equation by 5, again on the left, the 5 in the denominator would cancel. On the right, we would get negative 2 times 5, which is negative 10. You'll find that the moves that you do are the same because the left sides of both of these equations are the same. And then to finish, of course, add 1. In this equation, you get x equals 11, and then the other equation, you get x equals negative 9. So your first move is pretend it says equals and solve. Let's save those results so that I can, looking for my markers, so that I can clear the work that I just did in preparation for the second step. So we got x equals 11, and we got x equals negative 9. 9, 11. That's a little bit creepy or eerie that this problem that I randomly made up, and I did randomly make it up, gave solutions of essentially 9 and 11. And the day I'm recording this is, 9/11. All right, so we solve the equation, and then our second move is to partition. Now in class I said to partition the domain of the function, but I'm going to recant that, and for now just say partition the number line. truth is, in some equations, not every number is even an option, like a square root equation or an equation with a variable and a denominator, and you have to remove values that basically make the expression undefined or not real. But to make it simple at this stage, we'll say step 2 is partition the number line at these values. At these values. So we're going to take the number line, locate -9 and 11. -9 would be to the left, 11 would be to the right. And imagine the number line being a piece of string that we cut at those two pieces. And we're partitioning the number line at these values into intervals. And I remember when I wrote this in class, I had squeezed the phrase into intervals after partition the number line because I actually believe that that prepositional phrase fits better there. But regardless, you're cutting the number line at these values, you're thinking of it as a piece of string, and then you're describing the pieces of string that you get when you cut using interval notation. The leftmost interval would be -infinity to -9. Now we did talk about whether or not you use brackets or parentheses. In general, you should always use parentheses, and at the end you should just see if the endpoints work. But for this type of equation, you can just do what the inequality says. Since it says greater than, as opposed to greater than or equal to, we're not including the solutions, which means we're not including the -9. The next interval in the middle is -9 to 11, and the rightmost interval is 11 to infinity. So I partition the number line at these values into intervals, at which point we're going to test each interval using a value from each interval. I can't quite remember how I worded this last time, so here's how I'm going to word it now. Select a test value from each interval. Select a test value from each interval, comma, and test it in the original inequality. The original inequality. Each of these intervals either contains solutions or non-solutions. That's not quite what I wanted to say. Each interval is completely comprised of either solutions or non-solutions. For example, every number in the interval -infinity to -9 either makes the inequality true or it makes it false. It's not a mixture of the two. Same thing for the other two intervals. To decide which one it is, we simply have to test it by selecting a value. For example, in this first interval, we can pick any number to the left of -9. There's no need to get fancy, we'll just choose -10. For the middle interval, any number between -9 and 11, I would choose 0. For the last interval, any number after 11, I would choose 12. Your choice of test values is irrelevant as long as they're inside the interval which they're representing. And then we test them in the original inequality. So go back to the original inequality, substitute all the values one at a time, and pass judgment on whether the statement is true or false. If we test -10 in the original inequality, we get -10 minus 1 over 2, all inside an absolute value is greater than 2. Excuse me, the denominator was 5. The 2 is on the right side of the inequality. Let's go ahead and see if this one is true or false, and then we'll check the others. Inside the absolute value, -10 minus 1 is -11. And so we get -11/5 is greater than 2. Or rather, the absolute value of -11/5 is greater than 2. The absolute value of -11/5 is 11/5. And now we have 11/5 is greater than 2. And you may be able to look at that and see instantly if it's true or false. If for some reason you're having trouble thinking or seeing it, then perform the division. The left side says 11 divided by 5. 11 divided by 5 is 2.2. And at that point, it's pretty transparent that this test value makes the inequality true. And then we pass judgment on all the intervals via their test values. If we test x equals 0, we draw a line partitioning the board. If we test x equals 0 by putting 0 into the inequality, we get the absolute value of 0 minus 1 over 5. is greater than 2, without dilly-dallying, inside the absolute value we get negative 1/5, and the absolute value of negative 1/5 is positive 1/5. Positive 1/5 is not greater than 2. The statement is false. And similarly, in the third interval with the test value of x equals 12, we test it in the original inequality. So we'll set up the absolute value of 12 minus 1 over 5, put it greater than 2, and then try to figure out if it's true or false. It won't take you too long to figure it out because 12 minus 1 is 11. So we get 11/5, whose absolute value is 11/5. We end up at the same place we did here. And it's still true. So from each interval, select a test value, test it into the original inequality, and pass judgment on whether it is true or false. To finish the problem, the solution is the union of the intervals whose test values made the inequality true. Whose test values made the inequality true. In this case, the first interval was good. The middle interval was not. The third interval was good. And so our solution to this inequality is going to be the first interval, which was negative infinity comma negative 9, union the third interval, which was 11 comma infinity. So I don't want to say it's a long time consuming approach. It does have some steps where you have to spend a little bit of time evaluating things and passing judgment on truth value. But as a procedure, it's actually pretty straightforward. Solve if it's set equals, cut the number line into intervals, test each interval, keep the ones that made it true. In the next video, I will have already summarized this in this space over here using a lot fewer words. I'd like to do 1 or 2 more examples and 1 or 2 more videos.